So the next thing I want to talk about is multitask learning, and multitask learning is a technique of training a model to be good at multiple tasks and sharing some representations between different tasks. And that has one of its effects is that these representations which are shared are typically going to be regularized in some sense. They're going to be they're going to capture the properties of the data which are useful for multiple things, and they're going to be these different tasks are kind of going to mutually constrain the parameters of the model or the representations that the model builds to be something which is like good in general and not just good for one single thing. So from that point of view, it can also be thought of as regularization. So what you see here is a very schematic representation of this approach. What we have in this filled circle, this is the input data. Then this architecture has this shape of some kind of a fork. There is this circle which is labeled shared representation, and this is a part of the model which is shared between the two different tasks. And then this representation is kind of divided into two different task-specific portions. There is a representation specific to one task and another representation specific to another task, and finally there is some output. So what would be an example of this? So let's say that we want to do speech recognition and also at the same time recognize something about the speaker, whether they are old or how old they are, whether they are male or female, whether they are a child, or that would be another task. And maybe that we have yet another task which is determining some emotional valence of what was spoken, whether it was spoken with a positive attitude or a negative attitude. So some low-level representation of speech might be actually used by all of these in some way. And then for other aspects of these different tasks, probably we would want to have different representations. So typically it doesn't matter whether a man or a woman is speaking for the purpose of understanding of what exactly which words they spoke in which order. And likewise, whether the person was as a child or was a middle-aged, it also doesn't really matter. However, for some, it's at some level, at the initial stages of processing, we might want to have a shared representation which captures something which is important to all of these, and so that would be an example of a shared task scenario, of a multitask learning scenario. We're learning to perform multiple tasks while sharing some representations of the input and thus some of the parameters of the different portions of this architecture. And the next topic to mention in the context of regularization are ensemble methods. Ensemble simply means a combination of different things. Specifically, in the case of machine learning, an ensemble is a way of using multiple models to make a prediction. And so we can do something called model averaging, which is just combining predictions of different models in some way. For example, if you're doing regression, we can just take all the predictions of the different models and just average them. And for classification, we can do something like majority vote, so take the class which is predicted by most of the models. There is another ensemble approach called bagging, which we can do by randomizing some aspects of the training. So we can train k different models by sampling data from the training data with replacement. So all of these models are trained on different samples from the data. And for deep learning, we can also rely on randomization due to initialization and ordering of the data. So we can obtain different models, k different models, simply by randomly initializing them separately, and that already will give models which are different. We can of course also resample the training data in addition to that to kind of have two different sources of randomization. So why would we think that ensembling works? Well, it works because different models tend to make different errors. So maybe these errors are not completely independent, but at least to some extent they are different. And so the less correlated the errors, the better the ensemble will work. And so the intuition behind it is that by averaging the models, or taking some combination of them, we are relying on some kind of consensus. So it is unlikely that most models will make the same mistake on the same example. So if the models are kind of reasonable, they are not like they are not just completely random, but they are better than chance in some way. Then they will tend to be correct most of the time, and if they make a mistake, they will not all make the same mistake. Typically, not all of them are going to make the same mistake on the same data point, unless they're like very highly correlated, which is the particular case where ensembling doesn't work. So that's the intuition about it. And so we can see it in a simulation. So there are two in this simulation. I have created two models doing a regression task. So M1 and M2. And so in the plot we can see the true output that they were supposed to give, and on the horizontal axis, and on the vertical axis we have the actual prediction. So you can see that both of these models, the M1, which is green points, and M2, which are blue points, they're largely along this diagonal, which means that the predictions are correlated with the true values, but there is some error there. And I did another thing. I simply took the model, which is, I also plotted the predictions, which are simply the averages for each point of M1 and M2, and these points are in red. So if you, even just by eyeballing this scatter plot, you can see that the red points seem to be more closely along the diagonal than the red ones. Than the green ones or the blue ones. So there are fewer outliers, fewer points which are further away from the diagonal for the average model than for the two models which were averaged, which is the illustration of this effect of ensembling. And so just to make it a bit more explicit, what we can do, we can also plot the distribution of the predictions and of the errors. So if you look at the distribution of the predictions in these plots on the left, you will see that M1 and M2 have more spread out distributions, and the average of these two is more bunched towards the middle. And so these are just the predictions, but let's now look at the errors, and that's the plot on the right. And so in here, again, we have M1 and M2 with two different metrics, error measured according to mean absolute error and mean square error. And we also see these two metrics for the average model. And you will see that for both metrics, the average model the error is lower than for the models which go into the average. So just something as simple as taking two uncorrelated models and averaging them together gives us a nice improvement according to these two error metrics. So in the case of classification, it's we can also do a similar simulation, and here we will take three models, M1, M2, and M3, and they will have independent error probabilities. So they will make some error, but these errors are going to be independent in the sense that if model 1 makes an error, it doesn't mean that it increases the chance of model 2 making an error. They are independent. And then you will take a combination of these three, which is simply a majority vote. So it always this is a binary classifier, so it will always output the class which two of the other models agree on. And you will see here that the error here also, by taking the majority vote, decreases substantially, and that's because these models are have independent error probabilities. If that's not the case, remember that ensembling will not work if the errors of the models are highly correlated.